and I think the room is almost working. So we can start. The first lecture today is a presentation by Pedro Vieira about S-matrix bootstrap.
Okay, thank you very much. Thanks a lot for the invitation to this very nice conference. It's always a great pleasure to be at a conference where you know a little bit, a small corner, and then you learn so much. So it's how I felt during the week. It was great. So I'm going to tell you a little bit about some works that we have done with several people, but mostly with Andrea Guerrieri, Arish Murali, and João Penedones. And we started exploring this technique, the S-matrix bootstrap, which is a technique for carving out the possible space of theories. And actually, historically, we started first with QCD, studying pion physics and chromodynamic flux tubes, trying to develop the technique so that we could eventually attack gravity. But in the end, gravity is actually a bit simpler than QCD, at least conceptually, at least to explain. So actually, I'll start today with gravity, and at the very end, I will flash some slides to show you that we can also study and play with some questions in QCD using the very same techniques. And I'll try to be pedagogic and stop me at any moment with questions, and if I don't get far, that's fine, it's not a big deal. Okay, very good. So a question we could try to address with the S-matrix bootstrap, an example of a question could be, what can UV complete, say 10D maximum supergravity? Okay. So what could be the possible UV completions of a theory in 10 dimensions that has maximal supersymmetry? Of course, we know examples. We know string theory is one example, but we are agnostic and we just ask what could be the UV completion of such a theory? What could be an example? Now, this is a particularly nice theory. It's a theory in 10 dimensions. As you know, 10 is bigger or equal than 5. That means there are no infrared divergences. So as we heard in Luke's talk, if we have infrared divergences, then we have to struggle a little bit to describe what exactly are the good physical observables if we want to study things non-perturbatively, as we do. And the fact that we have maximum supergravity means that our amplitude, if I study our scattering amplitude 2 to 2, in principle, there is some tensor which carries the information about all polarizations. I like to write it as delta of Q. Some people like to write it as some R to the 4, indicating there is some tensor structure there. And that tensor structure dresses a function of S, T, and U, the usual Mandelstam variables, so that you have just one single function to study. If you want to study what is the 2 to 2 scattering process of, say, gravitons in this theory. Namely, you can scatter gravitons, dilatons, oxydilatons, everything in the supergravity multiplet, and they are all proportional to the same function, up to some tensor structure, and by extracting different components of this tensor, you extract different amplitudes that you can study. Okay? And so this is a big technical advantage that we don't need compared if we wanted to study, say, bosonic gravity, where we would have plus, plus, minus, 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 plus, plus, all these amplitudes, different polarizations, and so on. And here we have one single function to bootstrap to study the space of. Okay? So in 10 dimensions, this combination would be something like 60 some. I forgot the power actually. L Planck to the 8 probably. Yeah, L Planck to the 8. And often we'll set L Planck to 1. Okay, and so just to give you a so what do we know about this amplitude? So at low energy, this amplitude, we can extract, for example, a particular component out of this amplitude that multiplies, that out of this tensor structure extracts S to the 4, right? And just to tell you what this is, this would be S to the 4. This comes, as I said, from extracting a particular component, and I'll tell you what component it is from this tensor structure. And then at low energy, this amplitude, that is a symmetric function of S, T, and U. Of course, U is not independent. U is just minus S minus T. Right? We have S plus T plus U equals 0. S, T, and U are the usual Mandelstam variables, right? S is K1 plus K2 square, and the other ones are other Ks. So this would be the leading supergravity result. And then the first correction you would write is alpha. Okay, there is some powers of L Planck to make things dimensionless. So alpha is the first correction you could write, plus more suppressed in energy. And so this vague question about what can UV complete, what we mean by this spec question is what values can alpha take? Okay. So we start with supergravity, then we have the first correction, the first Wilson coefficient, then we have one loop effects, then the second Wilson coefficient, two loop effects, etc., etc. Okay? And we ask what is the possible space of this alpha here. So this alpha, for the specialists, this is some r to the 4 correction to the effective action. That would come with some coefficient alpha. And you could ask, why aren't there previous corrections? Why do we start so far? That's again related to supersymmetry. But there's actually a nice way to see it. So first, let's understand what component did we extract here. You see that if you look at this leading term, what happened with this? So S to the 4 over S, so I can simplify this and write S cubed over TU. But then, using that S is minus T minus U, this is minus S squared over T minus S squared over U, right? Just using that S is minus T minus U to further simplify that. So you see what happens. You have an exchange, a T-channel exchange, a U-channel exchange, no S-channel exchange, and the exchange is weighted by the energy square, by this S squared, so it's obvious that this is the oxydilaton that is being exchanged. So we have a scalar, it exchanges a graviton here, but there is no, but they are charged, so this would be the component for scattering. This is what we would call the oxydilaton. Okay, so this S to the 4 is a nice component, extracts these charged scalars out of the multiplet, and we could extract other stuff. Okay. Good, so we see that we have a spin 2 exchange of this oxydilaton. Now you could ask, okay, so what's the next term? Why did I jump from 1 over S cubed all the way to constant? Why don't I have 1 over S squared? Why don't I have 1 over S? So let's try to see. So let's try to see why here in the middle wouldn't I write something else. So suppose, for example, I want to write something that has at most poles in S, T, and U. It should be a fully symmetric function. It should have, this is one single function. So this function is symmetric in exchanges of S with T or with U. Right? It's a fully crossing symmetric function. So suppose I want 1 over S squared, I could write something like this. But of course, this is 0. And so there can be no such correction. This doesn't exist. What about S squared plus T squared plus U squared over STU? This would be the 1 over S term. But if you try to write such term there, then you would see by a similar argument to this that you would start having massless spin 4 exchange that you also don't want, and so you rule it out. And so, as we know well, with maximal supergravity, the first correction that you can write starts at order r to the 4. Okay? So that's the constant, and we ask, what is this constant? Okay? And the spoiler, okay, let me already tell you, that the answer is that alpha needs to be bigger than some alpha that we can compute from the bootstrap. And this alpha will turn out to be around 0.13. Okay? And that will be the result. And then the interesting thing is that if you can then ask, what about string theory? What value of alpha does string theory give? And it turns out to be a value of alpha very close to this value. And we find that intriguing. So what's the strategy for finding the space of alpha? The strategy goes in 2 steps. So there is an important step, which is, so if you want step 1, which is you make an ansatz for this function t, or a. Did I define t? Yeah, this stuff here with s to the 4 is what I call t. T is just a times s to the 4. So you make an ansatz for this t and a, and this is an ansatz with many parameters c, I, j, k. Okay? And the claim is that we have a big enough ansatz that we believe should describe all possible UV completions. And then, step 2, you minimize alpha subject to physics that you will impose over these parameters of your ansatz. And that's it. Okay? Okay, so those are the 2 steps of the bootstrap. Okay, so this physics, the key one, is of course unitarity. And unitarity here means what? It means that it means the following. This unitarity is the statement that if I decompose my amplitude into partial waves of spin s, so this would be I would call this the S matrix for an incoming state with energy S and spin L. So I start with a state that doesn't have definite momentum exchange, definite momentum, but it has definite S and definite spin. And of course, in the final state, whatever I have, this state will conserve spin, so it will have spin L. And if we do a 2-to-2 scattering, then it's the same state in the future. Okay? So if you are studying 2-to-2, it could be any state, it could be multiple particles. But if it's the 2-to-2 process, then it's the same spin L by spin conservation. And what is this guy? This is something that you get 1 plus I, there is some number, there is some power of s, that depends on the dimension you are in, and then there is some integral over the scattering angle with some simple Jacobian, then some Gegenbauer polynomials of this scattering amplitude times this amplitude t, which is a function of s. T is minus s over 2, 1 minus x, and u is minus s over 2, 1 plus x. So you see s plus t plus u is manifestly 0, and x is cosine of the scattering angle. And if you project the amplitude like this, you will project it into the various spins, and the condition is that the absolute value of this is smaller or equal than 1. Because this represents the probability of spin L going, a 2-particle with spin L going to 2-particle with spin L. You see, there could be many final states, so the probability that 2 goes to 2 is smaller than 1, because 2 can go to 2, to 4, to 6, to any number in the final state. Okay? I put a square here to indicate the probability, but of course it's smaller than 1. It doesn't matter if I put a square or not. Okay, so let me make a few simple comments. So one simple comment is that, you see, suppose you start with some 3-level approximation to your t here, And you ask, does this obey unitarity? And the answer is, of course, not. So you construct your t here, you integrate, you get something, but you will have this grow with s. Things will grow with s. And therefore, eventually, you fail to satisfy unitarity. You break unitarity. So these amplitudes, if you start truncating them, if you start writing an expansion that truncates, eventually they violate unitarity. So the fact that you impose that they satisfy unitarity for any spin and for any positive s will put very strong constraints on what you can write on this UV completion. Okay? And in particular, you cannot UV complete a theory that, for example, has alpha equals 0. If you put alpha equal to 0, and you try to ask that the higher terms do the job of unitarizing, you cannot, for example. So that's, you just try to put alpha equal to 0, try to complete the terms, and you just cannot do it. So you need alpha to be bigger than 0.13, as I will going to explain. Okay? Okay, the other important comment I just want to make is that the free theory, a free theory corresponds to this SL equal to 1, not 0. Right? That's just a free theory is a theory where the S matrix is 1. Right? So normally we always think, or you always think about the amplitude, which the S matrix is 1 plus IT, and then free theory is A equals 0, which is correct. And when t equals 0, however, the S matrix is 1 plus something, and this 1 survives. And that's the, and I say you because people that work in 2 dimensions, this 1 and t, they put them together, and they always work with S, and I often am in 2 dimensions, and there we often work with S matrix always. And so we start with a free theory here, and then it's the usual thing. You have some 3-level effect and some 1-loop effect, and that tells you to stay here. But then, if you really go non-perturbative, you go somewhere, and you better stay here or here, but you cannot leave this ball. Okay? So in perturbation theory, we start tangent to this circle, and we stay tangent to this circle. The 1-loop effect is what makes sure that we are in the circle. And that, and then as you do more and more loops, what will happen in perturbation theory will be sent inside a little bit. Why? Because you will start getting processes where, for example, you can produce 4 particles, right? At that moment, the probability, you start getting 2 processes where you will start seeing 2 to 4. And so there is a little bit of 2 to 4, and therefore 2 to 2 is a little bit smaller than 1, and therefore we are slightly inside then at, say, 2 loops or 3 loops. And then as you do perturbation theory, you move inside this circle, but you better stay always inside the circle. Okay, so that's unitarity. Okay, so that's the key physics you have to impose. And notice that there are 2 key physical conditions that you always impose, which is relativity, and in particular crossing symmetry, and unitarity, and of course analyticity. And you see that crossing symmetry is built in because I just say my function is symmetric, and then I don't worry about it. But unitarity is imposed. And analyticity, okay, it will be taken care by the ansatz, but I'm not discussing it yet. And this is what we have in this S matrix bootstrap. Now, just in case you heard, there's also this conformal field theory bootstrap, where people try to study the space of critical points of matter, so the space of scale invariant theories. And there, as you might have heard, I think, from several colloquia, what you do is you study the associativity of the OPE, of the operator product expansion. So there, you write a 4-point function. You say the 4-point function is a sum of exchanges, where here I have a structure constant, another structure constant, and C square is positive. In other words, unitarity is built in because we impose right away that C square is positive. But then we impose that this decomposition is equal to this decomposition, and so crossing symmetry is what is imposed. Okay. So there is a slight difference an important difference in practice on how the S-matrix bootstrap goes compared to this conformal bootstrap that is also very popular. Okay, so we started with 2. I told you about 2. So 2 is the idea of imposing this unitarity. Of course, we will do numerics, and we will have to impose it for any S. We will have to impose it for any L. So of course, there will be some cutoff here related to how many spins in practice do we impose. There will be a cutoff here, how many grid points in S do we impose. And we are doing numerics, so we will need to send all these cutoffs to infinity as best as we can. Okay. And so 2 is done. Let me move now to 1 and tell you, so what ansatz do we make for UV completion of amplitudes? Yeah.
You choose to scatter scalars because you have this freedom from supersymmetry, but do you get different constraints from different, by choosing to see different particles?
No. This guy, this single function describes everything at the same time. And you could even try to see what would happen to this probability for different components and so on. And everything would be exactly the same. And indeed, the reason is the following, is that if you would do unitarity fully supersymmetrically for all components at the same time, what will you have to do? You will have to ask, I have some amplitude, and here I have any possible amplitude. So it comes with some polarization for some in state going to some intermediate state. And then I glue it with another amplitude, and there is another delta Q for any intermediate state going to the final state. 3, 4. And then I sum over this intermediate state. And what do you get when you do this sum? We are just talking about the tensor structure in front to see what you would get. You get exactly the tensor structure for 1, 2 to 1, 2, 3, 4 times some S to the 4. Actually, I think this identity was written down by Zvi and collaborators. At least I think it's where I learned it from. And so when you do this, you see that you take these tensor structures, you glue them back, you reproduce it back, and so unitarity works just exactly for this function A, except there is some S to the 4 floating around, and that tells you that when you write unitarity, this S to the 4 shows up. And in practice, that means that if I study this amplitude that comes with this S to the 4, all I have to do is impose usual unitarity for this amplitude here. And I'll be describing everything. Yeah, of course.
So if you take S very large.
Yes.
Okay, so the term you wrote there, minus square over t, is precisely the leading order term of the amplitude, right, in the energy limit. And then what you get out of the rest of the expansion?
No, that would be terrible. If I impose that and if I just write that term, that would blow up at large energy. So the other terms need to fix that expansion. So the correct behavior at large energy of the amplitude cannot be just that. This UV completion changes the large energy behavior. This is correct at low energy only.
Okay.
Right, so this is a small s expansion. We are doing low energy. At high energy, we don't know. We have to be agnostic. We will now write what the amplitude should be. At large energy, it depends very much what we are doing. If we, we can form a black hole. So many things can happen. It's totally different at large energy. Low energy is under good control, of course. Okay. So the idea, and this is probably the key idea that we need for this ansatz, is what people call the rho ansatz, because there's some nice functions rho, and here it is. So the idea is to write t as basically s to the 4 1 over s tu plus, and now, so this is supergravity. The rest is the UV completion. And let's write the UV completion. So what's the UV completion? The claim is the following. I can just write a series up to infinity of some constants C, I, J, K. These constants are symmetric in I, J, K. That is making sure that we have crossing symmetry built in, as we said. And then these constants can multiplied by rho S to the I, rho T to the J, rho U to the K. Okay. What is this rho? Rho is the following. So what are the analytic properties of this function in the S-plane? There is a cut at S bigger than 0. That's just a cut that represents that at positive energy I can have 2 particle states flowing, 4 particle states, right? We have all this stuff flowing here. And that starts at S bigger than 0. And our amplitude, say, think as a function of S, as this cut here at S equal to 0. So imagine I start at S equal minus 1, or minus L Planck square, and try to expand around that point. If I did a Taylor expansion around that point, that would be a bad idea, because if I expand around this point, it has radius of convergence that stops here. Right? I can just not expand. I start expanding, and if I did an expansion, I can do a Taylor expansion, but eventually when these circles reach this point, the expansion would stop. It would not describe the amplitude. And so the idea is to foliate the complex plane with a variable that does this, that maps the cut plane like this, that foliates the plane covering all the plane minus the cut. So there is a very simple function you can write. You can just write rho of z equal 1 minus square root of minus z over 1 plus square root of minus z. So look at this function. This function maps rho of minus 1 to 0, and then it precisely does that in the sense that these circles, these lines here, are mapped these lines, they would be just mapped in Z to a unit disk where I would have just circles here in the unit disk. And this top part of the unit disk, A, would be the top part here of the cuts, and the bottom part of the cut would be the bottom part of the unit disk. Okay? And this map sends a function of S that has a cut at S equal to 0 to a function in the unit disk Z. Okay? And so, but we have cuts in S, in T, and in U, so I just write a triple series instead of a single series. Okay? So the claim is that this describes any possible amplitude as long as I send my cutoff to infinity. Now, this is quite non-trivial if you think a bit about it, because we have S, T, and U. These are not 3 independent variables. These singularities are movable. So U is minus S minus T. So it's true that there is a singularity in U when U equal to 0, but U is not an independent variable. And when I write this, I'm kind of writing it as if U, S, T, and U, as if they were independent. So in mathematics, this is what's called an analytic extension. It's not analytic continuation, it's extension. I have a function of S and T, because U is not independent. U is minus S minus T. And I said, I want to go from S and T to S, T, and U. Right? Okay, can I do it? Can I take a function in some slice and go to a higher dimensional space write a Taylor expansion in the higher dimensional space without introducing singularities. Because it could be that when I do this triple expansion, in this extended space, maybe there are some singularities such that the radius of convergence in the higher dimensional space has a smaller radius of convergence. And then I would be doomed. So I need that going from the two-dimensional space to the three-dimensional space, that I need the radius of convergence not to shrink. And so there are theorems in mathematics about when you can do it. When can you extend from 2D to 3D? And the answer is, if you are dealing with some Stein manifolds inside some bigger Stein manifolds, this extension never introduces singularities. And this is the case that we are doing here. Okay, we could discuss disks are Stein manifolds. We have product of three disks. The condition S plus T plus U is a holomorphic constraint on these rows that it defines another Stein manifold. And so we are guaranteed not that to be able to do it. Now, in practice, this is our ansatz, but we don't do infinity. Of course, we put some n max, some cutoff, and then we have many free parameters, and then this n max, again, we have to send to infinity. And so we have in the end to play with this n, with this n, with this n, and then we just take this ansatz and we do, as I said, you just minimize alpha in the space of Cij, subject to this unitarity condition. And this, in practice, it's done using software called SDPB, which is a software that people in the conformal bootstrap developed. Okay. Yeah. I think I'm going too fast. Any question here?
So that limit 0.13 or that bound, what happens if you're in 4 dimensions instead of 10?
So we only did it in 9, 10, and 11 because it was the value where we had string theory to compare with. 4 dimensions, we have the issue that 4 is not bigger or equal than 5. We have infrared divergences. And I do struggle, for the reasons that Luke mentioned, to say what is the well-defined finite object I would start with. What object would I try to UV complete? I really think it's true that it's a serious question about what is the physical observable that is infrared finite and that has nice analytic properties. Of course, we know absorption cross-sections are finite, but they have crappy analytic properties. What is the one that is finite and that has nice analytic properties? I think that's a key question.
So you can't really say anything about the bound.
I can say nothing about 4 dimensions for gravity because we have infrared divergences. We can do bootstrap in 4 dimensions for theories that don't have infrared divergences, like massless pions, for example, but not for gravity. Yeah.
Why do you look for a lower bound on alpha, not an upper bound?
You could also maximize, and then you would find that there is no maximum, that the maximum is unbounded. So you would do minimum and maximum, but it turns out that there is no maximum. It's just a one-sided bound. Let me just mention that you could impose a toy version of this where you stay in this corner here. So if you stay in this corner, that's what's called perturbative unitarity. That's staying a little bit like I have my 3-level result and the 1-loop result better send me inside so that I stay in the circle and so on. And so if your theory has a weakly coupled limit like ours does at low energy, then you better recover perturbative unitarity. So this contains in particular usual perturbation theory, and we must see the 1-loop result in Sugra coming out and so on. But also you could ask questions about just imposing the conditions from imposing this perturbative unitarity. People also call it positivity, because in some variables it's about being on this side of this line. That's what's being positive. And these games are games that people play. They are much easier games to play than imposing this proper non-perturbative unitarity. But because you don't have this circle, often you get very bad bounds, because this is really crucial for us. So I think without this non-perturbative unitarity, I personally don't trust most of the bounds that people discuss. Very good. There's something more I would do. Maybe I'll do it. I'll just go over the slides. Okay, so Tiago, maybe I'll go back. I'll go to the slides now. Yeah, of course.
Supersymmetry. Can you still do the analysis for non-supersymmetric gravity and tension?
Yeah, non-supersymmetric in higher dimensions would be very doable but painful. But there's nothing conceptual going on. 4D, there is something conceptual going on.
But no one has done it?
But no one has done it, yeah, no one has done it. You see, I mean, you would do it, you will suffer a lot because you will have many components and you will have to, now you will have this unitarity condition will be a matrix and so on, and instead of 0.13 you will get 0.07 or whatever, and then you have nothing to compare with. So it's a lot of work, and yeah, so that's I guess why people didn't do it. But it's definitely interesting. And
I mean, you could try and do it in like d equals 12, and then maybe you don't find that there are any UV completions. Some dimension.
Yeah, that's true. I think people should explore more this S-matrix bootstrap in silly dimensions like that, higher, that there should be nothing, and see what it gives. Yeah, I agree. I think that's a nice problem. Yeah.
Pedro, so you talked about the perturbative unitarity, but isn't your bound perturbative, the string theory that you're finding perturbative?
No.
The bound you obtained through non-perturbative methods, but the theory itself, string theory, that you're more or less finding, isn't it perturbative?
No, the theory is not going to be perturbative. It will not be this bound in 0.13 is not what you get from Virasoro-Shapiro. It's really what you get for string theory at strong coupling. So G string is not small. L string is not much bigger than L Planck. So we are not doing perturbative string theory. Okay. Very good. So let me then show you what is the result of doing this numerical method. Okay, so in this box here in the corner, it's a summary of what I told you in the blackboard. So we have our amplitude. It's a unique function times some invariant structure. It's convenient to study one particular component for this oxydilaton, which just multiplies it by s to the 4, and we want to put a bound on alpha. We write an ansatz. We write supergravity plus some series in rows that I factored out some terms. You can ask me if you want why, but it's just a series expansion in rows with some coefficients c, I, j, k that here I call alpha, a, b, c. And then you project into unitarity, which is this condition here. Okay, that the partial waves for spin L are smaller or equal than 1. And then, as I said, there are a bunch of parameters. There is how many terms of the ansatz, how many spins you impose, and how many points in S do you impose. The number of points in S, it's very easy to take a huge grid and never worry about it. You can take a grid of 3,000 points, and 3,000 is infinity. But spin and N is really key. It's really important to take as many N as you can, and as many spins as you can. Now, the correct thing to do is what is done here. Let's look at these two middle panels. These are for 10 dimensions. So here in yellow is some N n is here. It is n equals 16. So you see you sum A, B, and C up to 16. So you sum up to 16 and you see that you get some minimum value of alpha. But this minimum value is not correct because we only impose some small spin. If you impose more and more and more spin, the minimum converges to some value. So that's the value. You cannot do better than this value. So that's the minimum value of alpha that you get with this ansatz. But then you improve the ansatz. You go here. And as you impose more and more conditions, your minimum converges to some value. And you repeat it for increasing n more and more and more. So that here you start here, you impose more spins, you go here. And you see where these curves tend to. And that's what's done here. Here we extrapolate in spin. And now in n, we see that they go, and we fit to see where they go to. And they go, according to our fit, to this window here, this green window here, which is somewhere around, in this case, 0, 1, 0, 1, with some error bars here inside this interval. And here we are in 11 dimensions. I don't know, I switched to the 11-dimensional plot, where M theory, for example, predicts that this value should be 0.1028. And so string theory, for example, and I'm going to show where this number comes from, tells you that the minimum value of alpha at strongly coupled string theory is 0.1389, and the value that we get here is around 0.1241. And so you see that we get values that are very much compatible with string theory in 9, 10, and 11 dimensions, which means that, and string theory here, when I say string theory gives this value, what I should say is that string theory gives this value or anything above this value. This value is what string theory gives at strong coupling. As I decrease the coupling, I cover all the values all the way to infinity, exactly like we do in the bootstrap. Okay, so those are the results, and you see it's very close to string theory. Now, what could it mean, the fact that it's very close to string theory? Does it mean that string theory is the only UV completion? No, it's just a number. It could be a coincidence. But it's nice that we try to study what's the possible space of UV completions. We get some range, and that range is more or less what string theory would allow. It's suggestive, at least. Of course, it's a number. Right? So we have to take it with a grain of salt. Now, let me mention something that I find quite cute, which is related to where could this small mismatch come from? Here it's 0.12, here it's 0.14, so there is a small mismatch. So what could we maybe try to see? What could be some conditions we could be missing or that could explain some mismatch? So let me first remind you that actually when you have these Wilson coefficients, you can extract them by doing some contour manipulations. You can read them as the Taylor expansion of your function, but when you have a Taylor expansion, you can write some contour integral, blow the contour, etc. And in doing so, you can relate alpha to an integral of the imaginary part of the amplitude over S. Okay? So that's just a true statement. Now, that immediately tells you by the optical theorem, this imaginary part is positive, that alpha is positive. So alpha positive was a very trivial bound. No computation needed. It was just, you write this dispersion, immediately it follows that alpha is positive. Okay. By the way, here is the plot of the imaginary part of alpha. These various curves are when we increase n max, so when it's converging, the curves go to this, so it's a nice curve. And let me just describe it here. So you see that there is a plateau, that these curves struggle to reproduce, but they reproduce. Eventually they converge to the plateau. The red curve is really honest numerics. They converge to this plateau, and then there is a bump, and then they go to 0. This bump, it's actually a resonance. So this would be a prediction for some kind of particle. It would be some gravity ball at some m Planck units. So it would be some particular resonance that would exist that people call the gravity ball. And this here, this discontinuity, here I'm plotting imaginary part of A divided by S. So that is reproducing precisely the one loop result of supergravity. The one loop result will tell you that the discontinuity is something like S log S. The one loop result is something like S log S plus T log T plus U log U You take this continuity, and you get just the discontinuity of the log, that is 2 pi I, so you get the plateau. And indeed, of course, the numerics eventually converge there, because as I said, any function should be reproducible by this. But you see that this function doesn't have any logs. If I expand this function around the threshold, this will have an expansion that will not have logs. It will have square root singularities. And so how can I reproduce logs? I can, it's fine, but I just need to sum many, many, many terms, right? And eventually it converges pointwise to the precise distribution. Okay, that's an aside, but let's go on. So alpha is the imaginary part. The amplitude I can decompose in partial waves, and so I can write the amplitude as a sum of partial waves and take the imaginary part partial wave by partial wave, and you get something like this, 1 minus the real part of the scattering matrix. Now, recall, free means S equal to 1. Now, absorptive, totally absorptive, let me call it black hole, would mean S equal to 0. That means the probability is 0. You send 2 particles and you get 0. There is 0 chance that you get the 2 particles in the final state. So here is a toy model you could do. You could say, imagine I scatter 2 particles against each other, and if I scatter them at high energy, and if they are scattering inside the impact parameter of the Schwarzschild black hole, then they would form some black hole, and then the chance of producing 2 particles in the final state is 0. Okay? And so we could say that when S is bigger than S star of L, what is S star of L? Is this value here. This value is found by equating the impact parameter, which is this quantity, to L over square root of S, something that you guys know much better than me, to the Schwarzschild radius with that corresponding energy. You impose this and you find that at this critical S, I would be inside the Schwarzschild radius, I would form this black hole. And so you would say that at that point, this S would be 0, and therefore this integral gives me some 1 over S star to the 7. Now, it's a semi-classical guess, so when do I start? I start this game at some L star. So this could say, okay, alpha needs to be bigger than starting at some critical value, where I say like spin 10, it's already semi-classical enough. Then I should get this. So now I can plot this curve. And I don't know if you can see because of this blackboard, maybe not. But okay, it's a curve that just goes down. It starts, if I start imposing this constraint at L equals to 2 or something, I would say that alpha needs to be bigger than 10. That's huge. It violates, it will rule out string theory and so on. It's terrible. String theory was 0.14. But if you were to impose it at, say, spin 6 or spin 8, then indeed you would need to impose some condition in alpha that would give a mismatch of the order of 0.1, 0.01. That is precisely of the order of magnitude of the kind of numbers we get. So it's totally plausible that imposing some extra conditions, such as this one, could make these bounds even closer to the string theory bounds. And so that is just some rough estimate of what we get. So now, when you get this constant, you can get more than just a bound. If you get this constant C after the minimization, you get the full amplitude. And you can plot it in these unit disks, which means you are plotting it in the complex plane, and therefore you can look at its singularities, see resonances coming in, and so on, and study all the analytic properties of the amplitude you might want. And so the punchline is in this box here. So we studied better and better and better ansatz trying to extremize alpha, and we went down more and more and more and more. We extrapolated, we said we are more or less here, and string theory covers more or less the result that the extrapolation gives. Alpha from dispersion relation we know is positive, so this is forbidden. And so there is this gap of unallowed theories, and what is allowed seems to be more or less what string theory allows. Now, just to review what string theory gives, in string theory, we actually know what this alpha is. Alpha is what's called an Eisenstein series in type 2b. In type 2a, alpha is given by some simple expansion of G coupling. And this Eisenstein series, if you study it, it is a bounded function, and the minimum value is this zeta function, this value with some zeta functions, which evaluates to this 0.3 that I told you about before. And this is attained at a strongly coupled point when tau is e to the I pi over 3. Now, what would be very interesting, and it's something that Andrea, Arish, Elisabetta, and Kellyanne told me that they are doing, is to go beyond just studying the leading Wilson coefficient and study more than just the leading Wilson coefficient. Because this was just a number, but wouldn't it be much nicer to study the space of, say, the two Wilson coefficients, for example, alpha and beta in string theory? We also know what they are. They are both, in this case, given by some Eisenstein series, so you could draw what curve do we get in type 2b, what curve do we get in type 2a, and then we could ask, what would be the bootstrap, what region would we get? And of course, if we get a region similar to this region here, then it would be really a strong evidence that string theory would be the only UV completion. Then it's not just a number, it's a full map of an allowed region or not. Of course, this is wishful thinking. I don't know what's going to happen. My guess is that it's going to approach this gray region in some corners, but not everywhere. That would be perhaps too good. So finally, to conclude in the remaining 3 minutes, let me just tell you something about QCD. And I decided to just tell you about, to highlight a recent paper that Andrea wrote with 2 collaborators, Kellyanne and Sue. So that's not, this is not at all my work, but it's a work that I find really beautiful. And so in this work, the strategy, the idea is the following, okay, so we have this technique for writing ansatz for amplitudes that are supposed to be non-perturbative ansatz. Let's use this ansatz for phenomenology. So let's take physical data, like physical phase shifts of pions that you can compute here, 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 various phase shifts for some pion scattering amplitudes, and let's try to fit these phase shifts as well as possible, but with a very physical ansatz, which is this rho ansatz. So we take this rho ansatz for the amplitude that we are certain that it obeys crossing symmetry, that it has the right analytic properties, and so on. And let's try to fit the amplitude such that this amplitude, such that we try to fit an ansatz, such that we fix some parameters of the ansatz, like some scattering length, some mass of the rho particle, and so on. And we will try to fit it, but with an ansatz where we impose that we try to extremize this ansatz, subject to unitarity, and so on. So then we are sure that whatever fit we get is compatible with crossing symmetry, unitarity, and so on. I mean, because often what people do is they see some plot of some spin 2 and they fit some Brett Wigner or something without worrying about how it will affect other spins, whether it will screw up unitarity, whether it will screw up crossing symmetry, and so on. And you cannot just take spins independently. You need to fit everything consistently at the same time. And so you do this game of trying to fit, and here are some results that there are 2 amazing plots in that paper. And let me finish with those plots. So the first one is this one here, where you see that this is the total absorption cross-section for pi-pi scattering. And the blue curve is the fit of the S-matrix bootstrap amplitude. And what's cute is that there is this region here in gray, and that's the region that was used to do the fits of the amplitude. So you use this data point to do the fits compatible with crossing unitarity and imposing the known mass of the rho particle and so on. Outside this gray region, there are these extra experimental dots from all these experiments here. And this is not fitted, but the curves, when you go out of this region, many orders of magnitude in energy, they do kind of go nicely close to this result without imposing them at all in the fit. And this is the hardest region for the bootstrap. As we go to higher and higher energy, it's the numeric struggle more and more. But the one I found really cute was related to this spin 2, isospin 2 channel. You see that you get these experimental points that go down, 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 and you try to fit something that goes through these points. But you have to fit this curve, as I said, compatible with crossing, unitarity, and so on. And so let me show you what the fit of this curve, of these points going down, 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 down is. if you do it in this way, where you write a crossing symmetric ansatz and so on. And so here is the fit. So you see that if you impose that the fit is compatible with all this, you predict that, wait, actually these points are going to flip down, they are going to flip, and there will be a resonance, there will be a particle that they call some tetraquark, given the quantum numbers, at some given mass or with some given decay channel. And this is from a slide of Andrea, that there are people trying to look now for this particle here. So this will be an example where an S-matrix inspired parametrization, the S-matrix bootstrap parametrization, trying to describe physical data, tells you that, okay, all this physical data you have, if I put it consistently into an amplitude with the right analytic properties, this guy needs to flip, it needs to go up, and so there better be a particle there. So I find that super cute. So here are my comments, but you can read them. And maybe to end with a cautionary note, I think the bootstrap, I think, is a very powerful tool for studying non-perturbative questions. There are questions that when we are in a non-perturbative regime that I don't know of any other method that can address them because it's non-perturbative, so we cannot just use perturbation theory. If we want to start to put bounds on, say, locations of the chiral zeros of pion amplitudes non-perturbatively, I don't know of any other tool. But everything I said today and everything that has been done roughly, I mean, there is maybe one exception or two, was about 2-to-2 scattering. And this is really a huge obstacle to overcome. If we want to try to claim that to use the bootstrap as a tool, that you can make packages that are to really make it into an alternative to more standard quantum field theory, we cannot just stay with 2-to-2. We need to do 2-to-3 and so on. And it's very hard. So whether that big obstacle will be surmounted or not is a big question. But I think it's a method worth playing with, and in particular, it would be nice to bootstrap things that you care about. Thank you.
Thank you, Pedro, for this very lively presentation. We have a little time for a couple more questions if you want.
Thank you, Pedro. I actually have two disconnected questions. The first is precisely on this point of 2-to-3 and 2-to-4, where at least the matrix structure in supergravity is not that horrible. I mean, but somehow, from what you're saying, the impact of those in the supergravity should be minimal, because otherwise you'd rule out string theory. So do you have any sense of why that would be?
Yeah, so indeed, the effect of 2-to-4 and so on, they cannot be very big, because if the effect was very big, as you say, it would rule out string theory, which is already pretty much captured. So it's small. So we know they are more suppressed in energy, right? So it's less likely to produce 4 particles than 2 particles at low energy, so that partially explains why. The main challenge of 2-to-4 is not the tensor structure, it's the cuts. It's the analytic properties. Is that here I could say there is a cut at S bigger than 0. That's it. And if you do 2-to-4, good luck. I mean, if you do non-perturbative, even in 2 dimensions, even for 2-to-2 scattering, but when you scatter not the lightest particle, but you scatter some particles that are not the lightest, even then we don't know the analytic properties completely, let alone higher particles in higher dimensions. So that's an important conceptual question. What are the analytic properties of non-perturbative amplitudes beyond 2-to-2? And I think we just don't know. It's too complicated.
And that actually leads into the other disconnected question, which is, I'm assuming that the cross-sections have bad analytic properties because you're taking an absolute value of.
Yes.
But what about things like energy-energy correlations or other things? What are the problems with those kinds of?
No, energy-energy correlators is something that people are trying to bootstrap. I think they are great. I have no problem with energy-energy correlators. I think they are great.
Any other question?
Their analytic properties are a little bit more complicated than amplitudes. They are not as clean as amplitudes, which are more on-shell quantities, but they are great quantities physically.
Hi, yeah, thanks for the nice talk. I want to ask you about the LHCb resonance and this work that you showed before. So I didn't fully get it. You do the pi scattering and then you get the low resonance that you have, or you use that to predict the tetraquark resonance. You know,
So you just use data, the red dots. So the game they play, I can tell you in a little bit more detail. So you feed the red dots.
which contains this low resonance there.
Which contains this, where you see some particles like the row resonance and so on. The row resonance is in the second panel. So you fit the red dots.
Right.
And then you predict that beyond the range of the red dots, there will be a new resonance there that was not in the particle data book.
But you
Now,
don't-
when you
sorry.
do these amplitudes, there are many things that you can do, that you should do if you are trying to describe realistic pi-n amplitudes. So, for example, you take this SL, and one thing you should impose, for example, is that SL equal 1, isospin equal 1, at the mass of the row should be equal to 0. So that's the condition that you have a particle, you have this resonance, which is the row particle that we know very well. It's a very well-defined resonance. And that should manifest itself as a 0 of the S matrix at that point. Now, this is something a bit unusual. People are usually think about this, the resonance as being poles, not zeros of the S matrix. But that's just because they are poles in the second sheet, right? So when you have a pole in the second sheet, let me remind that you have a pole. The pole is here somewhere in the second sheet. That manifests itself by having a 0 in the first sheet, which is where we are. And the reason is that there is an elastic region where you are, where you have elasticity, where you have that S matrix in some region times the S matrix in the crossed cut is equal to 1. So that tells you that the S matrix in the second sheet is the 1 over the S matrix in the first sheet. So when the S matrix has a pole in the second sheet, you better have a 0 in the first sheet.
Right.
This is a relation you derive in a small segment, but once you derive this relation, you can continue it everywhere. And so one thing you can impose is you impose stable particles. So you fix your ansatz, imposing, for example, some particles that you know are there very well. So you see that that's what is there. It's constrained by, so you maximize some objective, constrained by, for example, this S11 big 0 for some particles. You also impose that the amplitude has some zeros at some particular values. Z0, Z2 that you don't know. These are what are called chiral zeros. So it's just the fact that the theory is derivatively coupled, so the amplitude should have some zeros near 0 and 1/2 that Weinberg computed. Now, all these values then, M rho, Z2, Z0, and so on, are parameters. You don't know what they are. So what you do is you then vary over those parameters, and for each such parameters you get some amplitude. And then you fit the data by scanning over these parameters so that the amplitude is the closest possible to the data.
Right.
So the fit only has like 8 parameters or something to fix all this data. So there are, it's not a fit with like hundreds of parameters. It's a fit with a relatively small number of parameters that you explore this 8-dimensional space by checking where in this 8-dimensional space am I closer to the physical amplitude.
Right. And my question, yeah, sorry.
Very quick.
Yeah. And my question is, can you predict the other resonance which are mesons, or you only predict theta quarks? In the sense that, I mean, could this theta quark be, or this state be more of a molecular state, or is really a theta quark?
No. You of course reproduce the existing particles. So here in this plot is what they presented for their determination of many particles. So they impose some of them, like the rho particle, perhaps they impose. But then this F2, for example, comes precisely on the nose with the particle data book. This higher energy one, it fails a little bit, the bootstrap. This one is new, this is the tetraquark. This one is precisely where the particle data book gives, but with the smaller error bars. So you impose some resonances, and then you see that your amplitude needs to develop more resonances, and you look at where they are the locations, and they better reproduce the known spectrum of mesons. Yeah.
Okay, let's have a very last one, unless you want to skip a copy, Rick.
Just a very general question. Can non-perturbative bounds be violated perturbatively until you resum? I mean, if you try to check with low-order loop calculations, can you actually sometimes violate the bound?
Probably, but it will be a bit tricky because when you are doing things perturbatively, so if you take the one loop result of some theory or the two loop, then it will be a Taylor expansion. Now you are telling me I truncate and I put a number for the Taylor expansion instead of thinking tangentially to the point. So that is illegal, right? But we do it all the time. But then, yes, indeed, so we stay tangent to the circle. But if I use one loop with a big coupling, I go out of the circle, I go here. Right? So one loop tells me you go to the circle, but if you are infinitesimally close, if you extrapolate too much, then no, you are here.
Okay, let's thank the speaker again. And who's next, Leonardo?